Hi, ladies and gentlemen. My name is John Belkowitz. I am the Director of Research and Development at Intelligent Concrete, where we specialize in concrete research, development, education, and litigation work. Today, we are going to be talking about hooked fibers, a very interesting subject, especially when it comes to the shear capacity of concrete beams. And we've got one of our customers is writing an article about this that should be featured here within a week or so, but wanted to go over it just a little bit of detail so we can refer back to this video for some illustrations. And if you look in ACI 318, which is this building code that we use for concrete design, it gives you this really quick and dirty equation for the shear capacity of a reinforced concrete beam. And what I've done here is I've drawn a single reinforced concrete beam. I guess you can make a double reinforced concrete beam that is simply supported, has a span of X, and we have a distributed load, and that distributed load could be your combination of your dead load and live load, your furniture, you know, the people walking in and out, permanent furniture, semi-permanent furniture, the mechanical stuff in your building. But it's all supported on a slab, and we can say that slab for a second is either made up of simply supported beams, or this is actually a one-way slab. Now, the shear capacity of this reinforced concrete element is based on a lot of things, but what the concrete brings to this overall structure is based on this equation, where it's R2, I believe that's a lambda, times BW, or the base of that section, times the compressive strength, times the D, or depth, to the middle of the reinforcement package that you have in the extreme fiber of the concrete. Now, what you should notice that there is nothing in this equation that refers to the steel. So this equation is basing the shear capacity totally on the material properties of the concrete and the geometry of our section. But here's the catch. If we take this non-standard concrete in this equation and all of a sudden we add these hooked-in fibers, we boost up our shear capacity of that concrete element in our compression as well as tension zone by 33%. We take that 2 to a 3. And the question is, why the heck does that happen? Again, we're not doing anything different. We're applying the same load. So if we look at this beam, we have a non-fiber reinforced side and this hooked-in fiber side, and we zoom in on it just a little bit, you know, so we take this section here and we look at it, what happens is when we have this triaxial state in one of our, you know, if we zoom in on an element within this beam, you know, we have either our uniaxial compression, and then we end up creating compression in the other axial direction, and then we also have some shear. What happens is those hook end fibers, when we start getting cracks through here, those hook end fibers are actually going to absorb some of those catastrophic loads that would cause our rigid concrete structure that doesn't really allow for atomic dislocations. It's going to hold those pieces of concrete together, effectively toughening up our concrete element, allowing for a greater shear capacity. Yeah, so I mean that's really why we're seeing an increase. And with hooked end fibers, you can use them from anywhere between 0.5% all the way up to crazy amounts like 3 or 5% in a cubic yard of concrete. In doing so, you always have to take into account how that the amount of fibers that you're going to use is going to have an effect on the fresh properties of your concrete, and that goes to mixed design, but that wasn't the purpose of this presentation today. So if you have any questions, let us know. It's been awesome talking to you. Thanks for your time. Send us a direct message or throw us a message on one of our posts, but we're excited to talk to you again about this awesome subject. Go concrete, beat asphalt.